Module 7, Describing Chemical Reactions. The mole concept. We now have come to the section where we can actually count the atoms or molecules within a sample of matter. But first, I have to introduce a term that refers to a group of items. You are familiar with a term for a group of items called a dozen. A dozen means 12 of something, doesn't it? So if you have a dozen eggs, you have 12 eggs. If you have a dozen donuts, you have 12 donuts. If you have a dozen kangaroos, you have 12 kangaroos. And a bit of craziness, too. Well, chemists have a group term for a specific quantity of atoms, and it has to be a pretty big number because you just cannot do very much with a dozen atoms. This group term is called a mole. A mole is 6.02 times 10 to the 23rd. So if we have a mole of atoms, we have 6.02 times 10 to the 23rd of them. If we have a mole of molecules, like water molecules, we have 6.02 times 10 to the 23rd of them. I cannot even think of having a mole, or 602 with 21 zeros, of kangaroos. Anyway, the word mole has to be big because we will always have lots and lots of atoms or molecules in a sample of matter. Say we had a glass of water that contained 12 ounces of water molecules. We could say there were 1.14 times 10 to the 25th molecules of H2O. Or we could take that number and divide it by 6.02 times 10 to the 23rd and say we have 18.9 moles of water molecules. Can you see that 18.9 is a much easier number to express than 1.14 times 10 to the 25th? It's like saying I bought 5 dozen eggs instead of saying I had bought 60 eggs. I can just take that number, 60, and divide it by my group number of 12 for a dozen of something, and I'll get 5 dozen. So we can use the word mole to help us better report how many atoms or molecules we're dealing with. Now this number, 6.02 times 10 to the 23rd, is a kind of weird number, isn't it? It isn't a nice round number. It's called Avogadro's number, after the Italian scientist Amedeo Avogadro, whose work led to its discovery. You see, Avogadro's number represents how many atoms are in a sample of an element when that sample has exactly the same mass in grams as the element's mass in atomic mass units. What do I mean by that? Well, look at the mass of a carbon atom. It is 12.0 atomic mass units. What I'm saying is that a 12.0 gram sample of carbon will have 6.02 times 10 to the 23rd atoms. The atomic mass of sulfur is 32.1 AMU. So a 32.1 gram sample of sulfur will have 6.02 times 10 to the 23rd atoms. So no matter what element you look at, if you have a sample of that element with a mass in grams that's equal to the numbered mass of a single atom in atomic mass units, you will have 6.02 times 10 to the 23rd atoms in that sample. 4.0 grams of helium, 52.0 grams of chromium, or 55.8 grams of iron all will have 6.02 times 10 to the 23rd atoms in each sample. I can sum all of this up by saying that 1 mole of atoms equals 6.02 times 10 to the 23rd atoms. And this relationship also works for molecules. If you add up the total atomic mass units of a single molecule, then if you have a sample of that number in grams, then you will have 6.02 times 10 to the 23rd molecules in that sample. Consider water. A water molecule has 2 hydrogen atoms and 1 oxygen atom. So its atomic mass is 2 times 1.01 plus 1 times 16.0, which equals 18.0 atomic mass units. Therefore, if you have 18.0 grams of water, you have 6.02 times 10 to the 23rd molecules of water in that sample. Or you can say you have 1 mole of water. All this means that 1 mole of molecules equals 6.02 times 10 to the 23rd molecules. Here are images showing a mole of each of these substances. There is a mole of water in the graduated cylinder because there are 18.0 grams of it. There is a mole of salt in the beaker because there are 58.5 grams of it. If you add up the molecular weight of 1 molecule of sodium chloride, then you can see it has a mass of 58.5 atomic mass units. So 58.5 grams of sodium chloride will contain 1 mole of that molecule. You get it? We have a mole of iron filings on the watch glass, which contains 55.8 grams of iron. 1 atom of iron is 55.8 AMUs. Finally, there is 1 mole of helium in the balloon, which contains 4.0 grams of helium. 1 atom of helium is 4.0 AMUs. But you have to pay careful attention to the questions you are asked so you know what unit to put on the atomic mass. The atomic mass in AMU will give the mass of 1 atom. The atomic mass in grams will give the mass of 1 mole of that atom. Additionally, we can say that a molecule's mass in AMU will give the mass of 1 molecule. The molecule's mass in grams will give the mass of 1 mole of that molecule. These are important points. You need to fully understand the difference between these amounts in atomic mass units and these amounts in grams. Because this is such an important concept, let's try looking at it more closely. If we look at boron on the periodic table, we can see that a single atom of boron has a mass of 10.8 AMUs. So that means that it takes 10.8 grams of that element to have a mole of boron atoms. You see, once we have the mass of a single atom or a single molecule, we know a conversion relationship that can relate the grams to moles of that specific atom or molecule. The conversion relationship will be different for each atom or each molecule, though. So if we want to know how many moles of copper atoms are in a specific sample of copper, we can use the relationship between grams of copper and moles of copper. Looking at the periodic table, we see that a single copper atom has a mass of 63.5 AMUs. So 63.5 grams of copper equals 1 mole of copper. Let's look at a few example problems together. How many moles of fluorine atoms exist in a 50.0 gram sample of fluorine? This is just a conversion problem, so we need to know the relationship between grams of fluorine and moles of fluorine. So look at the element on the periodic table. A single fluorine atom has a mass of 19.0 AMUs. That means that 19.0 grams of fluorine equals 1 mole of fluorine. This is a conversion factor, so now all we need to do is convert our given amount from grams to moles. What do we have? 50.0 grams of fluorine. Place that number over 1. Now what's the relationship between grams and moles of fluorine? 19.0 grams of fluorine equals 1 mole of fluorine. Set that conversion factor up as a fraction so that the gram units cancel. Now multiply through and we get 2.63 moles of fluorine. We keep the 3 significant figures because the 1 in the 1 mole of fluorine is an exact integer, not a measured amount, so we don't consider it when we look for significant figures. How about this one? People are encouraged to limit their table salt or sodium chloride intake to 5.000 grams per day. How many moles of sodium chloride is that? The problem is asking us to convert grams of sodium chloride to moles of sodium chloride. This is a conversion problem. We just need to know the relationship between grams of sodium chloride and moles of sodium chloride. So we need to look at the mass of a single molecule of it. It is 1 times 23.0 AMU plus 1 times 35.5 AMU, which equals 58.5 AMU. That is the mass of a single molecule of salt. So that means that 58.5 grams of sodium chloride equals 1 mole of sodium chloride. We can do our conversion by placing our original number of 5.000 grams of sodium chloride over 1. Then set up the relationship so that grams cancel and we get 0.0855 moles of sodium chloride. That number has 3 significant figures, so we are good. Let's take this problem one step further. How many molecules of sodium chloride are in a 5.000 gram sample? Well, we figured out that in that sample there are 0.0855 moles of NaCl. We also have a relationship between moles and molecules, don't we? 1 mole equals 6.02 times 10 to the 23rd molecules. So we can convert. What do we have? 0.0855 moles. Place it over 1. Set up the relationship between the units we have and the units we want so that moles cancel. Now multiply through and we get 5.15 times 10 to the 22 molecules of sodium chloride. The math here isn't very difficult. We are just doing conversions like we did at the beginning of this course. The challenge here is to understand what's going on. You need to remember the new concepts that the atomic mass in AMUs will give the mass of a single atom, and the atomic mass in grams will give the mass of 1 mole of that atom. And the same thing for molecules. If you catch that concept, you just need to do conversion problems to find your answers. But don't let the word mole confuse you. As long as you understand it's a group number, like a dozen, it will be easier to grasp. And we can thank Mr. Avogadro for it. Module 7, Describing Chemical Reactions. Experiment 7.1. In this experiment, we are going to do a lot of steps so that we can measure the width of a molecule. Now, you might wonder how in the world we can do that since we can't see molecules. Based on what we know about how atoms and molecules behave, we're able to do a series of steps and experiments so that we can determine the actual width of a molecule. So we're going to begin with taking some dish soap, and we're going to measure 5.0 milliliters into a graduated cylinder. So let me do that right now. This is just regular dishwashing liquid, and I'm going to measure 5 milliliters. Okay, so just so you can see, got 5 milliliters of soap in that container. All right, now what I'm going to do is I'm going to dilute that and with water up to 50 milliliters and do it very carefully because I don't want to create a lot of bubbles. So I'm going to tip it at first, kind of take some of the agitation out of the way until I get close enough. Okay, now I'm going to take a look here. Okay, so I've got 5 milliliters of dish soap and 45 milliliters of water that have been diluted. Okay, so now what we have to do is we want to take all of this and pour it into the glass. I'm going to gently stir it a little bit just to get the dish soap dissolved, because I want all of that dish soap in solution. And then I'm going to pour it into this large glass in front of me. Again, I'm going to tip the glass, trying not to have too many bubbles. Okay. I'm going to do the same thing, continue to dilute this by measuring out another 50 milliliters. You see some suds creating there. Let's let this down a little bit. I'm going to measure it so the suds are above that meniscus line, because there's not a lot of fluid there. And I actually need to do this 6 more times after this one. Okay, so I have added enough liquid water to the soap so that I've diluted that 5 milliliter measurement up to 400 milliliters of solution. And now what we're going to do is we need to calibrate our eyedropper. And what I mean is we need to know how many milliliters are in a single drop of water that comes out of our eyedropper. So to do this, we're going to take a clean graduated cylinder and our eyedropper, and we're going to count how many drops it takes to fill this cylinder up to the 10 milliliter mark. We'll use our dish soap solution to do that. So I'm going to start now and count how many drops go in here to make that 10 milliliters. I'm going to go 20 at a time to help me count better. $40. 60. We've got a ways to go, so I'm just going to keep holding on to it as I'm going to help it go easier. And then I'll put it on the counter when we get closer. Okay, that would be 80. That's 100. $120. And you know we can keep going on this until we get up to the 10 milliliter mark. Okay, so I finished adding or counting the drops to get to 10 milliliters, and I came up with 454 drops that equals that 10 milliliter mark. So what I'm going to do now is I'm going to divide the number 10.0, which is our milliliters, by 454, which tells us how many milliliters are in each drop of water. So let me take that 10.0 divided by 454. And I get 0.22, which really I have to round to 0.2 because I have 10.0 milliliters measurement. Okay, so 0.2 milliliters are in a single drop of our solution. All right, well now what we're going to do, we have a bowl of water right here, and it's just been sitting so that the water can become nice and still. I'm going to take some pepper and sprinkle it across the surface of that water, just a light sprinkle. You just want an even amount of pepper around the surface of your water. Don't sneeze while you're doing this. You don't want a whole bunch, just enough to see the pepper on the surface. Okay, now what we're going to do is we're going to take a single drop of our soap solution and drop it in the center. And what you're going to see is you're going to see the pepper move. It's going to create a circle of clear area where there is no pepper. I'm going to quickly try to measure the diameter of that circle in centimeters with my ruler. And we want to move quickly here, which is why I'm telling you what to expect ahead of time. Okay, I'm going to take one, I want to do one single drop and then quickly measure. And you want to measure the diameter. Get your head over the top, and it looks right about 11 centimeters. So I'm going to say it's about 11.1 or 11.2 centimeters of diameter there. And I'm going to write that down. Okay, what's happening here is there's a lot of chemicals in the liquid soap. All of those chemicals actually sink when they enter the water because they're more dense, with the exception of sodium stearate. Sodium stearate is more of a fatty material, and it floats on the surface of the water. And when I added it to the water, it started to spread out, similar to if you spilled water on pavement or something, it would spread out. The sodium stearate spread out along the surface of the water so that it got just one single layer of molecules thick. And now that's going to give us some measurement that we can do to calculate the area of a single molecule. Okay, so to do this, we're going to take the volume of that one drop of water, of soap liquid, and we're going to multiply that volume by the density of the liquid, which is 1.00 grams per milliliter. All right, and that's going to give us how many grams of the solution we added to the water. So we're going to take the volume of the drop times 1.00 grams per milliliter. 0.2 milliliters times 1.00 grams per milliliter. And of course, we're going to get 0.2. Our milliliters are going to cancel grams. Okay, that's what we have as the the number of grams of solution that was added to our water. Now, not all of that solution is sodium stearate, right? And so what we're going to do is approximately 0.0125% of that solution is sodium stearate. So we're going to take the number of grams we calculated and multiply that by 0.000125. That's a percentage, so it has no units. And so I have 0.2 times 0.000125. And I get 2.5 times 10 to the negative 5 as my answer. Okay, and that's approximately what we should be looking for, somewhere in that value, maybe a little bit even smaller than that. And if you get a number smaller, a little bit smaller than that, you're still doing good. Now, we have a chemical formula for sodium stearate. It's NaC18H35O2. We can actually take that formula and find the molecular mass of a molecule of sodium stearate. And I went ahead and used the periodic table and counted up all of those atomic mass units for all of those atoms involved. And I got 306.4 atomic mass units of sodium stearate. Make sure I get that right. 306.4. Atomic mass units. That's how much the mass of a single molecule of sodium stearate is. Now, what we can do is we can take that mass and we can convert the grams of sodium stearate, which we calculated here, grams of sodium stearate, to moles of sodium stearate. How do we do that? Well, when we have an atomic mass unit of a molecule, what that's telling us is 1 mole of sodium stearate is equivalent to this many grams of sodium stearate, and that's a conversion factor. So let me write that down. Okay, so let's convert the grams of sodium stearate to moles of sodium stearate. What do we have? We have this many grams. Let's write that down and put it over 1. Times our conversion factor. We want to set up our conversion factor so our grams cancel. So this 306 value is going to go in the denominator. All right, our grams cancel, and I'm going to multiply that through, and I have 2.5 times 10 to the negative 5 divided by 306.4, and I get, okay, my decimal place is to the tenths, so I have 8.2 times 10 to the negative 8 moles of sodium stearate. Okay, so that's how many moles that we have floating across the surface of the water, if you will. All right, now that we have that, we need to know how many molecules are in that circle. And so we know that each mole has 6.02 times 10 to the 23rd molecules in it. So if we take the number of moles that we have and multiply it by that number, Avogadro's number, then we're going to get the number of molecules in the sample. So I'm going to take my number here, 8.2 6.02 times 10 to the 23rd, and I get 4.9 times 10 to the 16 molecules in that number of moles. Okay, so that's how many molecules are in the amount of moles. They're floating across the surface of that water. That's how many molecules we have. Okay, so now it doesn't matter if we have every single step on the figured out here, or if you understand every single step, but just follow the logic through here. Once we have mass of the molecule, we can figure out how many moles that is. Once we have the moles, we can know how many molecules are there. And so now we need to know the area of a circle. Okay, I measured the diameter of the circle as 11.2 centimeters. That's how wide that amount of sodium stearate spread across. So I just need to know how much area that is. And so I just need to take the area of the circle, which is, of course, pi r squared. I need the radius, which is 11.2 divided by 2. My radius is 5.6 centimeters, and that times that squared times pi, which is 3.14, which we'll use. Okay, so the area of my circle, I'm just going to draw a circle here. .4 square centimeters is the area, using pi r squared as the formula for that volume. Now, we're going to take that area and divide it by the number of molecules in that area. How many molecules per area? So taking that area and dividing it by the number of molecules, 98.4 divided by the number of molecules, which is 4.9 times 10 to the 16. Okay, and what I get there is the area that each individual molecule takes up. Each individual molecule takes up 2.0 times 10 to the negative 15 square centimeters. That's how much space each molecule takes up. Okay, now that we have that information, how much area each molecule is taking up, we can estimate the molecule's width. Okay, we have to kind of assume that molecules are kind of taking up equivalent amounts of space, like little squares. And so to do this, we just take the square root of that area, and that will tell us one of the width or the length, if you will. So I'm going to take the square root of this, and I get 4.5 times 10 to the negative 8 centimeters. Okay. That's a little bit within the width of what we're hoping to find that your text tells us. That's very, very narrow. That's very tiny. In fact, that's tinier than the width of a hair. Notice that I was able to calculate the width of a molecule without having to actually see the molecule, using a series of steps and measurements that I could see and calculations that we have determined that help us know how molecules behave and the mass of molecules and the number of molecules that exist within a mole. So you don't have to understand the entire process of what we did, but just be amazed at how through calculations, a lot of indirect observations, we are able to determine the width of a molecule.
After doing experiment 7.1 and completing the on-your-own problems that come after it, hopefully you have a better understanding of how to deal with the concept of moles. But often, chemists will not convert from grams to moles, but the other way around. They have the number of moles in a sample and need to figure out the mass of that sample. Let's try that together. A chemist determines that a sample of pure ammonia, NH3, contains 12.331 moles of NH3. What is the mass of the sample? Well, we're given the moles and asked for the mass in grams. So we need to do a conversion. We need the relationship between grams of ammonia and moles of ammonia. So let's first find the molecular mass. 1 nitrogen atom times 14.0 AMUs plus 3 hydrogen atoms times 1.01 AMUs equals 17.0 AMUs. So we can say that 17.0 grams of ammonia equal 1 mole of ammonia. Now let's convert. What do we have? 12.331 moles of ammonia. Place it over 1. What is the relationship between moles of ammonia and grams of ammonia? 17.0 grams of ammonia equal 1 mole of ammonia. Set up that relationship as a fraction so that moles of ammonia cancel. Multiplying through, we get 2.10 times 10 squared grams of ammonia. We needed an answer with 3 significant figures because of gram mass having 3 significant figures, and we need to do that with scientific notation. You can see it doesn't really matter whether you want to convert from grams to moles or moles to grams. The setup of the math is pretty much the same. Why are we learning this? Well, think about how amazing this is. It is pretty easy to measure the amount of a sample of something in grams, but you can easily convert that measurement to determine exactly how many atoms or molecules you have of that substance without even being able to see those atoms or molecules. Avogadro's number is such an important one in chemistry.